focus on issues related to metal mining of copper, gold, silver, and other commodities. The extraction of these metals rely on a process called hydrometallurgy, where large piles of rocks called heaps, created from rubbleized ore, are irrigated with a chemical solution to dissolve the metal. If we move past the chemistry aspect of the problem, we are left with hydrogeology, as the makeup of the ore is essentially a porous media. Geophysical methods such as electrical resistivity are well suited to investigate hydrogeologically based problems, particularly because the irrigation solution in these mining operations is very electrically conductive. Over the years, we have investigated over 50 heaps and have seen patterns emerge in many of them that has allowed us to better understand their operational difficulties as it relates to removing the metal from the rock. A brief outline of my talk will first hit upon the goals of why we're doing this research. This isn't necessarily a pure scientific or research-oriented investigation. Our clients want to know how the leach pad is operating and potentially why they aren't hitting their target extraction goals. I will discuss the heap leach process and how the piles are created and irrigated, and then I will introduce the electrical resistivity method applied to imaging leach pads and provide several examples that cover issues of densification, that is, the compaction of ore from simple overburden stresses and from haulage equipment. I will finish with a summary of the presentation. I have mentioned that the heap leach pad can be viewed as a porous media that is irrigated from the surface. This is much like an irrigated field in agricultural settings. The media in the heap is to remain undersaturated for both stability and optimum extraction from a metallurgical standpoint. Therefore, we would expect that the hydraulic parameters that governs unsaturated flow will control the wet up of ore and extraction of metal with the goals to have as much ore wetted as possible, and for that wetted solution to drain effectively. Under a uniform flow situation, the accounting of extraction is simplified because only the efficiency of extraction under a particular flow rate is needed. This efficiency is taken from laboratory tests. However, we have seen that uniform flow is rare and that internal structure creates heterogeneities that will make flow through the heaps non-uniform. By using electrical resistivity imaging, especially in the early phases of the heap creation, we can mitigate potential problems that will be expensive to fix later on. A heap leach process consists of stacking ore that has been mined, likely from a large open pit, onto a plastic liner that collects the leach solution. Crushing the ore to enhance surface area is sometimes done, as well as agglomeration to create uniform particles. The ore is stacked in lifts that range in thickness from 3 to 30 meters and irrigated with drip or spray emitters to distribute the reagent. The drained metal-laden solution eventually makes its way to a pond and then to a processing facility to extract the metal. The metal-bearing solution is then recycled back to the heap. There are many heap leach facilities across the globe, and a 2014 report that is openly available on the internet has summarized basic heap operating statistics. There are 200 to 300 facilities worldwide, with the most common heap processing being used to extract copper or gold. New facilities are being opened or considered every year. For interest, I have included a map of heap leach operations around the world. In the U.S., these are mainly focused in the western states, and these states can be further divided into particular metal-focused areas. For example, Arizona is primarily a copper mining state, although some gold, lead, silver, and other metals have been mined here. Nevada is considered a gold state. Moving out across the globe, the focus of metal-rich ore is typically in tectonically active areas. In South America, many copper mines can be found at the intersection of the South American and Nazca plates in Chile and Peru. Heap construction and operation can provide clues to help us understand the heap hydraulics and perhaps develop specific methodologies for dealing with underperforming heap leach pads. At the top of the slide, I have a simplified schematic of a heap leach pad with 2 lifts placed on a liner. Many models for extraction use the simplified level of conceptualization for estimating production. In reality, the method of construction, placement, ore makeup, and environment play a role in how the reagent will interact with the ore. Stacking methods in the first column will affect ore density. Heap shape in the second column, whether on a flat surface or filling in a valley, will affect solution drainage and placement ore options. The lift height and grain size demonstrated in the third column may create structural non-uniformities that inhibit or divert solution from contacting all the ore. And lastly, the environmental conditions can play a role with extreme evaporation or excessive rains that dilute the reagent or frozen conditions that reduces the hydraulic conductivity. The chemical reagent used in the extraction of metal is applied at the surface through a number of methods that include drip emitters or some type of spray in an effort to ensure uniform coverage of the surface. For reference, the reagent used in copper extraction is sulfuric acid that ranges in strength from 3 to 30 grams per liter. For gold and silver, a dilute sodium cyanide of 50 to 500 parts per million is used. The application rate for the solvents are dictated by the ore itself to maintain unsaturated conditions to around 10% moisture. A common value for copper leaching in Arizona is 0.0025 gallons per minute per square foot. This equates to 6 liters per hour per square meter. Another factor in the application rate, at least for copper recovery, is the kinetics of the reaction. Kinetics governs the time needed for the reactions to complete. At the top of the slide, I have another simplified schematic representing a uniform percolation model, where irrigation is occurring from the surface and draining to the liner. I will come back to this in a later slide. In our simplified view of heap leach construction and operation, we have shown that the ore looks uniformly treated and placed on the leach pad. Additionally, the reagent is applied with an even distribution across the surface with tight control on the irrigation rate. This apparent uniformity then may logically bring us to a conclusion that the ore should be wetted uniformly. We can test this hypothesis by using electrical resistivity geophysics to effectively look inside the heap and ascertain whether the electrical properties, which are greatly influenced by saturation and ionic strength of the pore fluid, are also uniformly distributed. Fortunately, we can start using intuition to see that the uniform percolation is not actually happening. In several sites we have visited, we have observed ponding on the surface in isolated areas, meaning that the solution is draining through the ore in some areas, but not in others. On other heaps, we have seen seeps form on side slopes that may be several lifts below the top operating lift. And you see the photo in the upper right-hand corner. Excessive clays in a heap can severely limit drainage, causing a buildup of solution internally, then causing lateral flow towards the slope. A video in the lower corner shows water intercepted at about a depth of 50 foot during drilling. In our experience of investigating heaps, flow through the ore can happen in a variety of different means, and I have summarized some of them schematically in this slide. One flow model schematic that we would hope to experience is in the upper left corner, where the reagent is uniformly covering all surfaces of every grain. Theoretical chemical models used in hydrometallurgy that address stoichiometry, thermodynamics, and kinetics assume this to happen as well. Laboratory column studies where all flow is forced downward without opportunities of lateral flow reinforce this idea. However, at the field scale, uniform vertical flow is rare and the alternative is undesirable. The other 5 conceptual flow models presented here, while simplistic, gives a glimpse into the complications that large rock piles can create, such as short-circuiting, mid-level water tables, shedding to the slope, or a convoluted fish ladder-like flow. I have provided a list of causes here that can contribute to non-uniform flow that mainly create structural features that divert flow laterally, preventing drainage. Most items from the list are causes occurring at the onset of mining and placement. Friable material from a particular geology and mineralogy can break down easily during blasting, treatment, and stacking. A high initial application rate can cause fines to migrate or break down agglomerated particles, causing compaction or volume loss. Inadequate surface ripping and surface prep can prevent wet up in the first place. In the following slides, I'm going to focus on using the electrical resistivity method to examine issues of ore densification in older materials long after the mining and leaching has started. These materials are at the bottom of the leach pad and will be compacted simply from the weight of the overburdened material. A secondary densification issue is the use of heavy haulage equipment that is used in many facilities to transport and stack ore. One of the reasons we chose the electrical resistivity method for examining heaps is that the method has been well demonstrated to mapping variably saturated soils, similar to a heap leach pad. A conductive solution is then added to the top of the pad and percolates through a relatively resistive, initially dry media. And that most heaps have an insulating boundary condition at the bottom that is a plastic liner used to collect the leach solution. It is well suited to the problem. I will note, however, that there are complexities in using electrical resistivity data to understand the hydro and chemicodynamics of heaps. A case in point is the electrical resistivity section across a copper heap shown at the bottom of the slide. While we have been pushing for a uniform solution coverage model where we would expect the resistivity to also be uniform, I present a section that does not look uniform, but I would argue that it is a well-performing heap. We can distill the information into 4 distinct electrophases. Moira Poggi, my colleague, has a good presentation on the use of electrophases compared to lithophases for southwestern floodplains. The bottommost layer is the very resistive liner, and above this liner is an electrically conductive drainage layer that is highly saturated with significant copper sulfate concentration. The reagent in use to extract copper is sulfuric acid of a strength about 0.15 molar. The electrical conductivity of the acid is high, around 45,000 microsiemens per centimeter, and therefore the upper surface of the heap is conductive, but applied at irrigation rates that maintain unsaturated conditions. In the middle of the heap is a moderate resistive layer that still represents unsaturated media, but where much of the acid has turned to water, thus making it resistive. The draining solution has picked up copper and will continue to pick up copper while draining to the bottom saturated layer. A little explanation of the origins of densification issues presented here. Ore densification is a spatially and temporally variable. Over time, the ore can evolve naturally to become highly dense and prevent any vertical drainage to occur. Over space, the increased density can be highly variable based on initial grain size, agglomeration, or even weather. Crushing to get smaller grains may increase the surface area for increased extraction, but it can also lead to early densification of a heap. Heap height also plays a role, and routinely we see 300 plus feet tall heaps having compacted ore near the bottom of the leach pad. High density ore will reduce permeability. The resistivity profiles in this slide are from a number of different gold heaps in North and South America. All the profiles have a common theme where electrically resistive material in yellow and red is close to the liner. In the first example we showed, the material was electrically conductive above the liner due to adequate drainage of conductive solution making its way to the liner. Here we see that the conductive layer in purple and blue is actually in the middle of the heap, sitting on top of resistive material. In many of these examples, validation drilling or CPT analysis confirmed that an electrically conductive layer was a water table perched on highly dense ore. The water table can create dangerous conditions in the heap and make side slopes prone to failure. There are examples of failed heaps from perched water tables here in Arizona. Not all heaps have this level of densification. Here are 3 more examples showing how different the conditions in heaps can look, with the top heap being a crushed chalcopyrite copper ore. The middle is from a gold run-of-mine heap, also known as a dump, and the bottom is from a crushed ore gold heap. Each line also has a portion of it being actively irrigated, as indicated in the sections by a very near-surface conductive layer. One particular aspect of gold leaching, as shown in the middle profile, is that the chemical reactions and conductivity of the reagent does not play a role in the resistivity distribution. The resistivity distribution is mainly affected by saturation levels and the presence of clay. Switching gears just a bit to haul roads. All heaps need to transport ore to the top lift for stacking. In many cases, that haulage depends on heavy equipment that can be transported up to 400 tons of material per load. The roads over which the equipment traverses is usually fixed and used often. Then, the dumped material in piles will be spread with dozers. Water trucks will wet the roads to keep dust down. All of this haulage leads to compaction, starting at the surface where the roads exist, as opposed to densification issues described above that start deeper in the leach pad. Some leach pads have permanently placed haul roads that stay in the same location with the life of the facility. Other roads are semi-permanent or temporary and removed once the area of the heap is completed construction. We have used the electrical resistivity method on many different haul roads to show how damaged to the operations and removal metal these roads can be. Mapped examples of roads across heaps were taken from time-lapse images in Google Earth. In these two examples, there are haul roads that remain in a fixed location for years, as indicated by the overlapping colored lines. Then there are the temporary roads that are gone within a year. Fortunately, we have taken electrical resistivity measurements across all types of haul roads to show comparison of their effects on ore densification. In this slide, we present 3 examples of haul roads on heaps and the resistivity data collected on them. In our usual coloring of contours, low resistivity is in blue and purples, high resistivity is in orange and red. If a liner is present, it will be shown with a line marking its location. The upper profile was collected across a copper run-of-mine dump. When going back through time, we observed a haul road across the dump in 2007 when the first lift was placed. After about 250 feet of ore has been stacked, we acquired data in 2017 to investigate conditions prior to an injection program. The haul road is located in the center of the line, and the conditions are extremely resistive immediately below it. On either side of the haul road, the hydraulic conditions show a more uniform, wetted structure. The surface was being irrigated at the time of acquisition, and we are observing no drainage through the high resistivity material. Assuming a 0.3% copper in the ore, that leaves about 10 million pounds in this small section. The middle profile shows a gold heap with a haul road that was permanently located at about 250 meter mark along the line. Again, we see the heap is resistive below the surface all the way to the liner, equating to about 1 million cubic meters of material and potentially 40,000 troy ounces. On either side of the haul road, the hydraulic conditions are much different, validating the damage caused by the haul road. In the last example, we examine a semi-permanent haul road, or one that has been there for some time but didn't exist at the beginning of the heap construction. We observe the familiar pattern of high resistivity values to the liner, right below the roads. We hypothesize that the haul road's effects extend deeply because of the cyclical and vibratory stresses that the haulage equipment imposes on the roads. In summary, dense ore will not wet up due to lower permeability. In the resistivity data, we have identified dense ore at the bottom of the leach pads where the overburden stress has compacted it. Dense ore that is dry will have values of high resistivity and generally lower resistivity where the reagent is present and the ore is wet above it. In some instances, the wet ore becomes saturated because the ore cannot drain effectively, thus creating a perched water table inside the leach pad. These perched water tables can create problems by capturing and diluting the reagent, increasing the time of recovering the metal, and making the heap unstable. In a second problem of densification, we have investigated the effects of haulage equipment have on the leach pad. The cyclical and vibrational stresses causes compaction deep within the leach pad, as indicated by highly resistive ore surrounded by otherwise low resistivity wet ore. These haul roads can have high economic consequences, leaving behind a significant amount of metal that can add to tens of millions of dollars. Thank you.